In this video, we're going to quickly talk about Newton's second law of motion. Newton's second law of motion relates to the mathematical equation force equals a mass times acceleration, or F equals ma. What does this equation mean and how does it work? And let's go through some context behind it and then some mathematical equations for it. What this equation says is if I have an object, any object is a block, it has some mass. When I talk about mass, I'm talking about m in the equation. If I want that block to move, I need to push it. So I need to apply a force. Talk about force, I'm talking about F. And if I push that block, it's going to move. And if that block moves, it must be accelerating because at this time right here, the block is not moving. And at some point into the future, it is moving. So there must be an acceleration because the block has gone from a speed of 0 and now it's having a speed of 1. So the block has accelerated. So it has an acceleration. So that's where this A comes into it, the acceleration. We're going to apply some logic behind this equation and then relate how this relates to the mathematics and doing the calculations behind it. But let's start with a block, and I want you to imagine it's really heavy. It has a lot of mass. It's really heavy. Big block, it's a truck. If I try and push that truck, it's not going to move because it has a lot of mass. It's too heavy for me to exceed the frictional force which is holding it in place for me to push it. If I took a car, and let's just imagine that we've got enough force to push this truck, to push this block that has enough mass, it's going to start to accelerate once you exceed the frictional forces and the things that are holding that truck in place. So it's going to start to accelerate. But I want you to think about whether or not it's going to accelerate quickly or whether it's going to accelerate very slowly. And because we've got a large amount of mass, I want you to think about the acceleration rate. If there's a lot of mass, it's going to be really hard to push it, so it's going to accelerate very slowly, i.e. a big truck taking off from the traffic lights is probably going to accelerate very slowly. If I have a small mass and I have the same amount of force pushing, it's going to be easier to push that object because it doesn't weigh as much. So with the same amount of effort, it's going to take off at a greater rate. So the acceleration will be more compared to before. I can apply this logic across to the varying the amount of force. So I've got my block. I want to think about what happens if I apply a large amount of force. Or a large push. If I push the object really hard, it's receiving a lot of force which is going to cause it to accelerate, which is going to cause it to accelerate quickly. So it's going to accelerate quickly. Now, if I apply a smaller push, I'm not pushing as hard, so clearly it's not going to move as fast or take off as fast. If I don't kick the football as hard, it's not going to go as fast, it's not going to accelerate as fast. So it's going to accelerate slowly. I think that's about what I wanted to cover in that. But we're going to talk about this relating back to this equation just here with numbers. So now in a different colour, I want to go through these examples before, but we're going to put numbers into it. So we're going to use the equation F equals ma. But in this example right here, I want the mass to be a really big number. Truck. Trucks weigh a lot. So let's imagine that the mass is a big number. 20 tons. And a ton is 1,000 kilos. And for today, we're always going to be measuring the mass in kilograms. So the truck has a mass of 20 kilograms. If I push it as hard as I can, let's imagine that you can push 50 kilos worth of weight. If I convert that to a force, which we're going to learn how to do soon, I need to think about the force of gravity exerts a force of 10 meters per second squared. That's the acceleration of an object due to gravity. So the total force applied is 500 newtons. It's okay if you don't understand that step. We're not going to be exploring this explicitly in year 10. But if I push that truck with a force of 500 newtons, which is about as hard as a human can push, this equation must equal the same on both sides of the equation. There's a 500 on this side of the equation, which means this other side must be 500 as well. 20,000 times something has to equal 500. And that number is going to be very, very small. Very, very small. And it turns out that number is 0.0025. Just 1 0. And this number here was representing my A value. And I just want to talk about why this number is so small, so that both of these numbers equal 500. We've got a truck. Trucks have a lot of mass, so it's going to accelerate very slowly. And if you have a look at the acceleration number, it is indeed accelerating very slowly when we push it, assuming that there's no friction. If you compare that to a mass that's very small, pushing a push bike or a trolley. Same situation, we're pushing a trolley that only weighs 20 kilos, but I push it with the same amount of force that I push the truck, still 500 newtons. 20 times something must equal 500. I think it's 25. And this 25 is talking about the acceleration number. It's accelerating at a rate of 25 every single second. It's accelerating much faster compared to the previous situation. And hopefully the reason for that is common sense. This object is much less in mass compared to the original, so it's a lot easier to accelerate it, which is why this number is so much larger than this number. This object weighs less, so it's easier to accelerate it. This object has more mass, so it accelerates more slowly. If we apply this to how hard you push the object, the same thing applies. If I push very hard, 500 newtons, and I'm pushing that same 20 kilo trolley, it's going to accelerate at a rate of 30 meters per second. But if I only give it a small push, I'm not pushing as hard. So let's imagine that I only push with 100 newtons of force. In order for this side of the equation to equal 100, we can't change the mass. The object still weighs 20 kilos. The acceleration value must change, and in fact the acceleration number drops. In this situation, when we push it very hard, the object's accelerating at a rate of 30. But when we don't push as hard, 100 newtons, the object doesn't accelerate as much. Okay, let's go through an example, and we're going to go through that same process that we went through in our previous two videos, where the first step is to maybe draw a picture and identify what's happening in the situation. And to do that, I draw a dot in motion type questions, you need to draw 2 dots for the start and finish. For Newton's laws of motion, you only need 1 because we're not talking about what happens into the future. Here's my object. I'm pushing it with 10 newtons. That's a force. The object has a mass of 4 kilograms and it'll have some form of acceleration because it'll zoom off that way. But I don't know how fast it's going to zoom off that way, how much its speed is going to change by. Step 1. What are we trying to find? Find the acceleration. So we're finding A. My units for A, go to your formula sheet, meters per second. That's just speed in reference to time. That's why there's a square term there. I'd go to my formula sheet and now identify the formula that we're going to use to find acceleration. If it's to do with motion, you'll use the motion formulas that we've used previously. If it has anything to do with force, just jump straight to the F equals ma equation. In this equation, it helps me find F. I don't want to find F, I want to find A, so I need to rearrange this equation for A. To do that, I need to divide both sides of the equation by m, so that m cancels, and you're left with A equals F over m. The harder I push something, the more it accelerates. The more mass something has, the slower it accelerates. I'm pushing with 10 newtons of force, and the mass I have is 4 kilograms. 10 divided by 4. Write a sentence about your answer to make sure it makes sense. The object accelerates at a rate, or the object's speed increases 2.5 meters per second every second. Okay, we'll do one more example and then you can have a go at the worksheet on the following page, and there is an extension page on 26 for those that are wanting a little bit more of a challenge. Question 2, what net force is required to make something that weighs a ton, 1,000 kilograms, to accelerate at 4 meters per second squared? Step 1, what are we trying to find? How much force does it take to push the car? So we're trying to find the force. And force is measured in something called newtons. Because it has to do with force, we're going to use the F equals ma equation. I'm making substitutions, so I'll put in my brackets. And we're talking about a car, so I need to know how heavy the car is. I'm pushing the car, and when I push the car, it's going to start to accelerate. And it says the acceleration is 4 meters per second squared. When I finish doing this example, I might explain what that value there represents as well. So accelerating at a rate of 4, and the mass was 1,000. So in order to do this, the total force would be 4,000 newtons. Now, some of you that are into your cars and things like that will have heard of something called torque. Torque is measured in something called Newton meters, which is a force applied from a certain distance. Hence the word meters there, so 1 meters. A force applied from a distance of 1 meters, which is twisting power. So torque is twisting power. So this force just here could be applied, and depending upon what length of the axles are and the gearing ratios, etc., etc., you could work out how many newton meters of torque the car has to accelerate. But when we're talking about torque in the car, we're talking about twisting power. Trucks require a lot of torque because they have a lot of mass, so you've got to pull a lot of mass. If we're looking at horsepower in a car, that's talking about how much energy the engine of the car can produce every second. So the energy produced per second. And that's required for that determines your top speed of a car. So they are interconnected. For example, at the moment, there's these electric cars. At the moment, they have incredible amounts of torque. They can accelerate from 0 to 100 in 2 seconds flat. So they have incredible acceleration, but they don't have the horsepower to reach a high top speed. So they may be incredible with their acceleration. They're not so incredible with their horsepower. So the conventional cars that we have today, supercars, still have a much greater top speed than the traditional or up-and-coming electric vehicles. Okay, so from here, can you please have a go at today's task? I did say before, previously, that I would say what this value over here means. And if I wanted to convert this into kilometers per second per hour, it would be more relevant. And remember, I said to convert this across, you times by 3.6. And when I times that by 3.6, I get 14.4 kilometers per second per hour. So this situation just here means if you were looking at the speedo of your car, and right now the speedo was reading 0 kilometers an hour, if you looked back in one moment into the future and we started accelerating, we put the pedal down on this car, this needle's going to start to move upwards. The speed's going to start to increase. So if I looked back in 1 second, the speed would then be 14.4 kilometers an hour. And then if I look back in another second, it'd then be about 28, 29 kilometers per hour. We'll look back a second later, it's going to be over here. If I look back a second later, it's going to be over here. And it would keep doing that as the car accelerates through. Okay, that's it for today. Tune back in for our next lesson. I think we might be back at school next week, is my understanding. So class as per normal. Hopefully we can start to put some practice and things like that in for all of you when we get back to school. Most likely having a test sometime towards the end of the term.